Okay, hope everyone can see the screen and hear me as well. So this was the circuit, right, that I was showing yesterday. Why is the top panel not going? Anyway, doesn't matter. You guys can hear me all right, yeah? Yes?
Yes, ma'am.
Okay, good. So today's task is to just mainly analyze this circuit, and my job is to convince you that the state that appears out here, which is the last remaining unmeasured qubit in this 3-qubit circuit, is indeed the same psi which was intended to be communicated to Bob. Bharat. Okay, so this is the circuit picture, right? Is there a message on the chat? Okay. If there's a message, please speak up. I'm not able to see the chat so clearly today. Okay, so we have these. So the cartoon picture would be just so that you don't get confused, right? This A1, A2 are both qubits in one lab, right? What I said, Anita's lab, right? So this is Anita's lab, and this is Bharat's lab. Okay. At the beginning of the protocol, they share an entangled state, right? And this could be, for example, those pair of entangled photons that we described yesterday, the polarization entangled photons, right? So at the beginning, they both share this entangled state. Sorry, my WebEx is acting up again today. Okay, fine. So at the beginning of the protocol, they both share this state, right? And this is the state, one of the 4 Bell states that we wrote down yesterday, which is this beta 00, right? And the idea is that there is an additional state that is given to Anita somehow, right? And this additional state is psi, okay? And her task is to communicate this additional state to Bharat without really destroying the state, and she just has one copy of the state, right? So how does she communicate this to Bharat? And the idea is that this shared entanglement between A and B is going to help them do this, right? And at the end of the protocol, like I said, the state completely vanishes from Anita's lab and appears in Bharat's lab, right? So at the end of the protocol, so this is the start of the protocol. At the end of the protocol, there is no psi here, but there is psi here. Okay, so let's see how this works. This is just, like I said, a toy picture of this protocol, right? But this is the actual circuit. So this is just a schematic. I just want to mention a little bit about the history of this, but maybe I'll do that at the end after we analyze this protocol. So actually, I want this circuit to be seen prominently. Anyway, so now the way I'm going to do it is I'm going to start writing down states at various points of this protocol. Okay, so I'm going to first say that the state that we start with, is someone speaking? Okay, the state that we start with is what I'm going to call psi naught. Okay. Note that these are all going to be tripartite states. So they are states on A1, A2, and B. So 3 qubit states, right? And then after the C naught, we're going to call this as psi 1. After the Hadamard, we're going to call this as psi 2, right? And then the measurement happens, and then we're going to show that This part, let's just, maybe I should have spoken about this. So let's just look at this part, right? So like I said, the two lines means classical communication, right? So the double line indicates that some classical bit is being transmitted. So this M1 and M2 are classical bits. They are the classical outcome of these two measurements, the capital, which I've labeled as capital M1 and capital M2. Note that they're all measurements in the 0-1 base, right? And conditioned on these two bits, right? Depending on what M1 and M2 are, Bharat has to do some local operation on the qubit that is at his disposal, right? His half of the entangled pair, he has to do some local operation. And what is that local operation? So this is what I denoted as x raised to m2 and z raised to m1, which means that if m1 is 0, there is no z. If m1 is 1, there is a z gate that he has to do. And if similarly with m2, these are what we will call local gates in Bharat's lab, right? These are local gates that he has to do in order to complete the protocol. Okay, fine. So let us start looking at these states one by one now. So what is the initial state psi naught A1, A2, B? I hope you all work this out with me. Okay. So remember that this is actually psi A1 tensor beta 00 A2B, right? This is the Bell state, and this is the so-called unknown or arbitrary single qubit state. Okay, so let's write this out explicitly. So this is of the form alpha 0 plus beta 1 tensor 1 over root 2 0 0 plus 1 1, right? So if I were to combine all of this now, this becomes 1 over root 2 alpha 0 0 0, right, plus beta 1 0 0 plus alpha 0 1 1 plus beta 1 1 1. Okay, and the order of the labeling is always A1, A2, B, right, for all these 3 qubit states. So these are all now 3 qubit states that I'm writing down. Okay, so this is the initial state at the start of the protocol, right? Note that there is no entanglement initially between A1 and A2B, correct? A1 versus A2B is a product state. A2B, of course, is an entangled state. This is the one of the Bell states. But there is no entanglement across this cut. See, when I have a multipartite system like this, right, so there are associated Hilbert spaces A1, A2, A3. Now, you can have bipartite entanglement across different cuts, right? And they could be unentangled across different cuts. So that's what is happening here. Across this cut, they are unentangled, but these two are entangled. That is the initial state, right? When I say entangled, it's not the, I mean, the initial state has this form that it is unentangled across this cut. Okay, all right. Let's keep this in mind. So this is the first step. The next step is the psi1 state. So psi1 A1, A2B is the state, remember, that you get after the action of the C0, right? So the C0 acts between the first and the second qubit. This is the A1 and the A2 qubits, right? So what does it mean? Whenever A1 is 1, A2 is going to be flipped. Okay? So can you quickly work out what this state is going to be? And then I will write down what I have and you can check if that is correct. Please work this out with me. Okay, is this right? So remember, this is alpha 0 times 0, 0 plus 1, 1. And there is no change to the second and third qubits at this point, A1, A2, B. I'm just writing out the state in different ways, right? And then beta 1, now wherever there is a 1 on the first qubit, the second qubit has to be flipped. That's the C naught action, right? So this has to become beta 1 times 1, 0 plus 0, 1, right? And the third step, okay, is everyone clear with this step? This is after the action of the C naught. Let me call this 1, and this is after C naught. Then there is 2, is after C naught and Hadamard. Yes. So what is this state? So this is side 2, A1, A2, B. And this again is simple to write down. It's a local Hadamard only on A1, right? The Hadamard is only on the first qubit. So that becomes alpha 0 becomes plus, right? So that is 0 plus 1 by root 2. So I'll take the root 2 out. So I get a half, right? And then this is still 0, 0 plus 1, 1. And then plus beta 0 minus 1 by root 2. I've taken the 1 over root 2 outside. And then it is now 1, 0 plus 0, 1, right? Okay. So far, so good.
Yes, ma'am.
Okay. So now I'm going to group the terms somewhat differently because pretty much the gate operations are done in the circuit. Now we have to look at what happens after measurement, right? Now, which are the qubits that are being measured? Only A1 and A2, right? The two qubits in A's lab are being measured, right? And then we have to show that when these two qubits are measured, this 3-qubit state is such that B's qubit, that is Bharat's qubit, will automatically be in the state alpha 0 plus beta 1 up to some local gate operation, right? Okay, so let's see how that comes about. And it's just a matter now of rearranging the state, that's all. So I'm going to now group the A1, A2 terms together, okay? So you can of course expand this. How many terms are there? There are like, 16 terms here, right? So I'm going to group this in the following way. Basically, I'm going to group it according to the two possible outcomes of A1, A2, right? So one possible outcome is 0, 0, right? A1, A2 being 0, 0. Now, which are the two states where A1, A2 are in state 0, 0? So let me use maybe different colors to show this. I mean, I can just write down the state, but I don't want to do that. So note that I'm now going to group A1, A2 together and the corresponding B that accompanies that. Okay. So A1, A2 is both 0, 0 here, right? Remember, this is A1 and this is A2 and B. Okay. And what accompanies B at that point is kept 0, right? And here, again, I have A1, A2 both being 0, 0. So I'm going to write it like this. I have alpha 0, 0, 0 plus beta 0, 0. Yes, this comes with a 1. Okay. So this is one pair of terms for me. Then I have the next pair of outcomes that I can have for the first two qubits are 0, 1, right? So here again is 0, and the second qubit is 1 here. Again, here is 0. The second qubit is 1 here, right? So again, I have this form where it's alpha 0, 0. The second qubit is, alpha 0, 1 is what I wanted to write. Alpha 0, 1, right? maybe I should indicate here, this is A1, A2, and this is B, okay? Plus beta 0, 1, and what do I have here? I have a 0, right? 0, okay? The third possibility is to have 1, 0, right, for A1, A2. So where are the states where there's 1, 0? So this is 1. The second qubit is 0 here, right? This is 1, and the second qubit is 0 here. Okay? So I have alpha 1, 0. I'm just gathering the 1, 0 terms. So this is 1, the purple colored one, right? So 1, 0 comes with a 0, and there's a beta 1, 0. But note that now the 1, 0 here comes with a minus sign, right? So this is minus beta 1, 0. Okay? And what's the third qubit now when we have 1, 0, 1, right? Okay. So again, this is A1, A2, and this is B. And the final, the last color, I have a blue. Okay. So the final possibility for A1, A2 is to be in 1, 1, right? And when A1, A2 is 1, 1, 1, 1, right? The third qubit is also 1. Again, here I have 1, 1. The third qubit is 0. And you see now again this comes with a minus sign. So it's minus beta. So 1, 1, 1, 1, 1, right? Minus beta 1, 1, 0. Okay? Okay, so I hope this step is clear. This is the step which requires some attention. If you guys are finding this reading off like this somewhat difficult, what I suggest you do is to just expand the state out fully. Write out all 16 terms, right? So you'll have alpha 0, 0, 0, plus alpha 1, 0, 0, plus alpha 0, 1, 1, plus alpha 1, 1, 1, etc. I'm saying 8 terms. So write down all the 8 terms like this. You have 4 alpha terms and 4 beta terms, right? And then group them according to the first 2 qubits, right? Group them in such a way that you can sort of, the measurement outcomes become manifest, right? So basically there are 8 terms here, and some of them will come with a minus sign, right? Because of the Hadamard here, some of them come with a minus sign. So just keep track of that. Okay. So I hope this step is clear. Okay. So now I'm going to group this further, right? And write it like this. So now I have 0, 0 tensor alpha 0 plus beta 1. Okay, this is the first term. Then the second term in green becomes 0, 1 tensor alpha 1 plus beta 0. The third term becomes 1, 0 tensor alpha 0 minus beta 1. And the fourth term becomes 1, 1 tensor alpha 1 minus beta 0. Is this clear now? Because the first 2 qubits are 0, 0. So I can pull that out. And then I have a alpha 0 plus beta 1 on the third qubit. Here again, 0, 1 is common. That's how I've grouped them. And then alpha 1 plus beta 0, right? So this is A1, A2, and this is B. This is A1, A2, and this is B. This is A1, A2, and this is B, etc. Right? So now let's pause and observe what has happened, right? Look at the tensor product structure of this state now. Okay? Is it an entangled state? Is this an entangled state, this 3-qubit state?
Yes, ma'am.
Where is the entanglement?
Between like B and A2, A1 and A2.
Very good, indeed. Yeah. So you see, what has happened is, so how do I answer this question? Well, I look at A1, A2, right? And I see that there is a correlation between which state A1, A2 is in and the state of B, right? Similarly, here if A1, A2 is 0, 1, B is in a different state, which is alpha 1 plus beta 0. Here it's in alpha 0 minus beta. So there is, you see, in A1, A2 now, I have a set of 4 states which are mutually orthogonal, right? So the 4 states on A1, A2 are basically the orthonormal basis for a 2-qubit space. And the third qubit now is in one of 4 states depending on what A1, A2 are. So what has happened to the entanglement structure of the state? Remember, originally it was like this, that A1, A2 were not entangled. They were in some product state. And then there is entanglement between A2 and B, right? But now, right, the entanglement is actually between A1, A2 and B, right? It was not, so you can no longer write down this tensor product structure, right? It is not that it is factorized such that A1 is separate and A2B is separate. You cannot factorize it like that. Rather, there is still entanglement in this cut, but it is now tied to a state of A1, A2. So the entanglement structure of the state has changed, and that is that's what should happen, because what I have here is an entangling gate, right? I have the C0 gate. So the C0 does do something to A2 conditioned on A1, right? So actually, before the measurement, right, this tripartite state actually has, where is this? Yeah, so this is the tripartite state, right? So this tripartite state is such that the entanglement has actually spread out in some sense, right? It is no longer just entanglement between A2 and B, but this out here has succeeded in also entangling A1 with A2. And A2 was anyway entangled with B, so the entanglement is somehow now smeared across these 3 qubits, right? And the final act of this measurement is, of course, going to break the entanglement. It's going to break the entanglement between A2 and B and collapse you down to some specific state of B and some specific state of A1, A2, right? Okay, so remember that the last step is to look at the measurements now. So we've written up to psi 2, right? And I hope this part is clear, where I'm grouping the terms like this. So the final step, this was step 2. The final step is the measurement. It's the measurement of the qubits A1 and A2 in the 0-1 basis, right? Both in the 0-1 basis, right? So then what happens? Now I have to write down 4 outcomes, right? One of 4 outcomes is possible, right? So remember that the measurement M1 on A1 gives outcome little m1, and the measurement M2 on A2 gives outcome little m2, right? So I can now write down a table of sorts, okay, as to what M1 and M2 are and what the corresponding state of qubit B is, right? So I can write down a table of this form, and I encourage you to fill out this table yourself. You see A1, A2 being 0, 0. The state of B is alpha 0 plus beta 1. What is this state? This is exactly the state that you wanted to send over to B, right? So if the measurement outcomes are both 0, 0, which is the first case, then the state of qubit B is exactly the state that you want, right? That's it, you're done. But that is if you get the outcome 0, 0. And what is the probability that you will get this outcome? What is the
1/4.
1 by 4, exactly. So suppose there was no classical communication between Anita and Bharat. Suppose Anita did not use these two lines to communicate the information to Bharat. Then 1 out of 4 times, Bharat will have the exact state that Anita wanted to teleport. Right? So it becomes a probabilistic protocol. But if you want a deterministic protocol, where at the end of it, for sure, Anita has teleported the state to Bharat, then she has to communicate her classical outcome, because without that communication, it's only 1 in 4 times that B is going to have exactly this state, right? So the other outcome is 0, 1, and with 0, 1, the state in B is now alpha 1 plus beta 0. So what is the local operation that B has to do now to get the state, that original state?
Bit flip.
A bit flip, exactly. So if B does an X gate, so if B applies an X gate, right, then he will again get back the state alpha 0 plus beta 1. So remember, that's why we had said X raised to M1, right? So if M1, X raised to M2, right? That's what I said, right? Hope I didn't mix that up. Yeah, here you go. So X raised to M2. So if M2 is 1, which is the 0, 1 case, then B has to do an X gate, right? M1 is still 0, right? So these are both gates that have to be done in B's lab, right? So if M1 is 0 and M2 is 1, then the local operation that B has to do is an X gate, right? The third possibility is to have 1, 0, and if it's 1, 0, you see that B state is alpha 0 minus beta 1. And so what is the gate that has to be applied to get back?
C gate, phase flip.
Yeah, this is a phase flip indeed. Very good. So what B has to do now is a phase flip. So a Z gate has to be applied. And that's where this is Z to the M1. And the final possibility, of course, is that both the measurement outcomes could be 1, in which case you see the state is alpha 1 minus beta 0, right? So it requires both a bit flip and a phase flip, right? So both bit and phase flip gates are required. That's X and Z, right? Okay, so that's it. So that's the teleportation protocol. I hope the idea is clear. So they start with an entangled state, and A is given an arbitrary state, single qubit state, which has to be communicated to B, right? And basically they use the shared entanglement to end up in a state where, depending on A's local measurement outcome, okay, so measurement of A1 and A2, note, is a local measurement, right? And the gates that are applied are also local gates, right? So these are local gates to be applied in B. So these are local gates on B's system, right? So the reason that there is this correlation between the measurement outcome on A's end and the local operation that B has to do, the reason that there is this correlation goes back to the fact that they started by sharing an entangled state, right? So the protocol involves local measurement on A side and local gates conditioned on the measurement outcome at on A side. So this picture as such is incomplete because they not only share this entangled state, but they also have to share, yes, what else has to be shared?
Results of the measurement.
Indeed. So what has to be shared is two classical bits. So I also have to share two classical bits. Okay. So what I've drawn out here as a schematic can also be written as a schematic equation, right? So this is what is called a resource statement. Okay. So what the teleportation protocol achieves is to use one entangled bit. So the entangled bit, so this beta 00 is often referred to as one E bit, right? That is basically one entangled state. I know it's somewhat confusing terminology because an entangled state is two qubits at least, right? But this is a kind of resource statement that people like to make in quantum information theory. So what has been consumed and what has been achieved in this protocol, right? So that's what a resource statement for teleportation protocol will look like. You have consumed one entangled bit plus two classical bits. So these are called C bits. Okay, to get one qubit worth of communication, right? So the idea is that it is not necessary for A and B to actually have a communication channel between them, right? They need not have a quantum channel between them. Rather, what they need to have is the ability to share entanglement. And if they pre-share this entanglement, then just by using classical communication, right, they are able to achieve some kind of quantum communication. So that's what this resource statement tells you, that even if they don't have a quantum communication channel as such, but they have a way of sharing entanglement. Now, arguably, how do you share entanglement? You need to send quantum states. Finally, if you want to share entanglement between two distant locations, that is true. But in any case, this is a kind of resource statement that people like to write. Sharing entanglement is an important part of quantum, networks and quantum channels that people are building today in labs and so on, right? The other thing I want to point out about teleportation is that while the word sounds fancy and it appears as though the state has disappeared from A's lab and appears in B's lab, there is no faster than light communication. It is not instantaneous, right? Why do I say this? What do I mean by this? How would you justify this statement?
Is the delay being caused by the classical information that is being sent?
Indeed, exactly. So because a certain amount of classical communication has to happen, right? And this classical communication, as you know, is very much bounded by the speed of light, right? So the reason for this is because the protocol is incomplete without the classical communication. So there is no information transfer that is, so the information transfer is not instantaneous. So when I say not instantaneous, what I want to say more precisely is that the information transfer is not instantaneous. So as a communication protocol, right, you are really bounded by the speed of the classical communication, which is going to communicate the two classical bits. Is that clear? So we want to talk about the speed of the communication. This particular protocol is not achieving for you anything faster than the classical communication. So the speed, if you wish, is bounded by the speed of the classical communication of the classical bit, right? So this is again something important to keep in mind. So although it appears that there is some spooky action at a distance in play here, it is not so in practice, because in reality, or not just in practice, even in, fundamentally the information transfer cannot happen faster than light. So there is nothing spooky happening as far as the transfer of information or as far as the communication process is concerned, right? Okay, so any questions so far? So this completes the discussion of the teleportation protocol, and I think I've said all that I wanted to say about it.
Ma'am?
Yeah.
In the circuit diagram, we are mentioning like we are performing some conditional gate operation, right? Not
yes, the T not.
I mean at the last. So this X gate and Z gate is like more kind of a conditional operator. We are not performing it for every operation. Depending upon the post measurement, then only we are
Correct.
applying this X and Z gate conditionally, correct?
Correct, yeah.
So which means when I see the circuit, I got confused that always the X gate and always the Z gate should be applied, but it's not that, correct?
No. This is circuit notation that where whenever I have a measurement and I follow it up with two classical lines, it means that that's a conditional operation. So this you'll find often used in quantum circuits, where if I want to do a measurement and then conditioned on the measurement outcome, I want to do something else, I will usually denote it by two lines. They are supposed to be classical lines in the sense they are not carrying quantum information, they are carrying classical information, and that feeds into this X gate. So that's why I write this as X raised to M2 and Z raised to M1. Because when M1 and M2 are 0, there is no need to apply anything, right? X to the 0 is identity, Z to the 0 is identity. Right?
Okay. So this two line is something denote classical communication also with some kind of a conditionals which we can do.
Correct. It's what we call a classical conditioning, right? Remember, the control not is a quantum conditioning. Okay, because this controls the second qubit depending on the state of the first qubit. There is no measurement and communication happening out here, right? It's a kind of quantum conditioning, if you will. But this is a classical conditioning. This M1, M2 denotes classical conditioning because you're collapsing the state. The capital M1 measurement and the capital M2 measurement collapse the state. And there is a classical outcome, and that classical outcome is then deciding whether or not you do the X gate and the Z gate. Okay, I hope the contrast is clear. Okay, just want to conclude by mentioning a couple of historical nuggets. So the teleportation protocol itself is originally due to a whole bunch of people who are all sort of pioneers of this field. So this is a paper due to Bennett, Brassard, Pepu, Josa, Perez, and Wouters. So I will just say Bennett, Brassard, et al. Okay, and this is actually FISREV letter 1993. So I'll put a link to the original paper here. It's very readable, right? So this is volume 75. This is the page number. All right. So the protocol is already more than 20 years old now, right? It's going to be 30 years old soon. It was experimentally first demonstrated. So the first demonstration was using squeezed states of light. So I spoke about polarization entanglement. You can also have entanglement in the squeezed modes of light. Some of you physics guys may understand what I'm saying. Otherwise, don't worry about it. This is just for those of you who want to read up about experimental implementation, and this is due to Kurosawa et al. Again, I'll give you the references on Moodle. Hopefully by tomorrow, I'll populate the Moodle page. The other implementation is actually due to Nielsen and co-authors in NMR. So NMR, the qubit is a nuclear spin, right? And this implementation also is 98. So this is by Nielsen. Nielsen, the same Nielsen who co-authored Nielsen and Chuang, the book that hopefully you guys are referring to. Actually, the earlier implementation is actually the polarization states of light. So that's polarization entangled photons. This is actually 97. This is by a group in San Diego due to this optics guy called Baumeister, right? So this is all, as you can see, very, very old implementation. So this is polarization entangled states. So today, of course, I mean, people are doing teleportation across hundreds of kilometers. These early experiments will all be tabletop experiments, right? But now you can, of course, do this over hundreds of kilometers. And if you can, like China, send a satellite up in space and share entangled photons across thousands of kilometers, then obviously you can also do teleportation across thousands of kilometers, right? So that's just where we are today. The distance is clearly bounded by the distance over which you can share the entanglement, right? So the distance over which you can, where did I have the cartoon picture went off on top? Okay. Yeah, so the distance is essentially bounded by the distance over which you can share good quality entanglement. So like I said, in building so-called quantum networks today, sharing entanglement is an important problem for that reason. How do you share entangled states without losing, without them getting corrupted too much and so on? Okay. All right. So I have another 5 minutes or so, and in this, I want to start discussing something. Okay, questions? Let me again pause and ask.
Ma'am?
Yeah.
So for every qubit transfer, we have to share this entangled pair, a new entangled pair every time.
Correct. Yeah. You will lose one entangled pair in communicating this, right?
Okay.
Yeah. Okay. So actually, if I look at what I have shown, let me go back to this cartoon picture. So I want to introduce something else now. So if I have this cartoon picture and I say, okay, what have I done? These two guys shared an entangled pair. There was some state psi that was given to A, and that state has finally been sent to B by consuming this entangled pair. As Nilesh just pointed out, for every state psi that you want to send or teleport, you have to consume one entangled pair. So what is so remarkable about this, right? Why can't, for example, why can't A simply copy psi? Right? What is so special about this protocol? I kept insisting that, this is an unknown quantum state and A cannot measure, but maybe A can just make a copy.
Ma'am, there's a no cloning theorem, right?
Exactly. So that's what I'm coming to. So can A simply copy psi? The answer is no.
Ma'am, actually, like the copy is possible, but then the state that A has will be destroyed, right?
So that's not a copy, right?
Oh, right,
So,
right.
yeah, exactly. So that's what I'm coming to. So the teleportation protocol is not making a copy of the state psi, and indeed copying an arbitrary quantum state is forbidden by the laws of quantum mechanics. Okay. So cannot A simply copy psi? Well, the answer is no. And what forbids A from copying psi is the so-called no cloning theorem, right? This is a very fundamental result. So having shown one protocol which is somewhat remarkable, which shows how you can, simply make one quantum state disappear in one lab and appear in another lab, which is potentially thousands of kilometers away. I'm going to show you a no-go theorem, right? And quantum information theory has several of these no-go theorems, okay? So this should now destroy the illusion that quantum information and computing are all powerful. They are not all powerful, okay? They have some severe restrictions, and tasks which are very simple in classical information actually can become impossible in quantum information, right? So the low cloning is a classic example of that. So the no cloning theorem itself is due to Wouters and Zurek, and I think this is 1983. It's a Nature paper. Again, shall post it on Moodle. Okay. So the no cloning theorem says that an arbitrary quantum state psi, and let's for example stick to qubits if you wish, although the statement is of course much more general, cannot be copied. So more formally, how do I conceive? So if I were to state it somewhat differently, I would say these are equivalent statements. There does not exist a universal quantum copying machine. Okay. The word universal being very important here. Okay. So what does one mean by that? So again, I keep telling this to students. I guess you guys, some of you may have not even come to campus yet. You don't even know what Guru Nath is. But those of you who have been to campus and who know what Guru Nath is, Guru Nath was at some point famous for its Xerox machine, right? Where thousands of reams of question papers and assignments have been copied, notes, class notes, right? Using this amazing Xerox machine of Guru Nath, right? I think Guru Nath is no longer even there, probably. Anyway, so the point is that in classical information, we are used to having a nice, universal Xerox machine such that you send in your class notes. Okay, this is the paper that I want to copy, and this is an ancilla state, right? I'm just trying to now make a quantum copying machine, right? So what would a quantum copying machine look like? At the very least, it must have two registers, one with the information to be copied. One is a blank sheet of paper, the blank state in which the information must be copied. But of course, no friend is going to give you his or her note if you tell them that every time you make a copy, the state is going to be destroyed. Okay? So at the end of the protocol, you want to see your friend's notes survive unscathed, and you want also a copied state. Right? So this is what an ideal quantum copying machine must do. And what I'm going to show you tomorrow at the beginning of class is that such an ideal quantum copying machine does not exist. Okay? I don't want to start the proof now. It's going to take me 10 minutes, and I think it's not fair to start that now. But I just want to put this idea in your head so that you can think about it a little bit. Okay? So what I'm going to show you tomorrow is that such an ideal copying machine is not possible. Okay? Maybe the formal statement would be that, so the state that is to be copied is not just one state, right? I want to copy my friend's notes. I want to maybe copy the notes for another subject. There are like 5 different slots, A to G slot. I want to copy notes, right? Now, so the point is I want to be able to do the same thing for another state phi, for some other state chi, right? So the precise statement, and of course, I put a U here. Why did I put a U here? What does that indicate?
Universe.
Or is it unitary?
Exactly, yeah. So this operation, what quantum mechanics tells me is that this operation has to be a unitary operation, right? So Siddharth, you had a question, you can speak up because I'm just going to wind up the class right now and I'll continue the proof tomorrow. So maybe I'll just mention one last thing. So the statement is that if two states psi and phi are to be copied, then either the inner product of psi with phi must be 0 or the inner product of psi with phi must be 1. These are the only pairs of states that can be copied perfectly. Which means that psi, inner product psi with phi is 1 simply means that psi is the same as phi, right? So either psi is the same as phi or psi and phi are orthogonal. These are the only states that can be copied perfectly. Okay, let me stop here. Is there a question? You can speak up. Siddharth, you had typed some question.
Excuse
No,
me,
ma'am.
ma'am.
Yeah. So you were put the same thing, unitary matrix. Yeah, I see your question. Yeah, indeed. Yeah. Since quantum gates and quantum circuits are unitary operations, so the only the only thing that is allowed is a unitary transformation, and that's what we'll show tomorrow in class. That if this constraint you impose that U has to be unitary, then you will end up with this statement. Okay, that only orthogonal states or the same state can be copied by a given machine. Okay. Yeah. Was there another question?
Yes, ma'am. In the
Yeah.
section of teleportation, you
Mhm.
started with an arbitrary qubit state psi, but there is no specific restriction that the psi has to be a state of a qubit. I mean, psi can be any arbitrary state, like it can be the state vector for two entanglement qubits. So in such a case, how would the teleportation protocol take place?
Oh, so you're asking if psi itself were one half of some entangled state, is it?
Not specifically one half of an entanglement set. I mean to say that psi can be anything, right? Means it need not be a pure state, but rather it can be anything which is, I mean, any quantum state. So in such a case, how would the protocol take place?
Yeah, that's again a good question. I think somebody already asked me about mixed state entanglement yesterday. Was that you? I don't know. But yeah, so if psi were a mixed state, which means that psi were a density operator, then this protocol does not go through like this. Okay? Because a mixed state is a mixture or a convex sum of a certain set of pure states, right? So if you give me a mixed state, you have to tell me what is the pure state decomposition. Then what I can do is to teleport each pure state in that decomposition. Okay, that I can do. So, but to teleport an unknown mixed state as such cannot be done perfectly. Right? This is now perfect, right? Like the psi has been exactly recreated here. Right? Assuming everything is ideal, assuming the circuit is ideal, I have a way to exactly teleport psi. That can never happen with a mixed state. I cannot do ideal mixed state teleportation. Okay, that's a good question. Yeah, it cannot be done. But you can do it with some fidelity, what is called fidelity. You can do it up to, you can approximately do it, let's say. Okay, I'll see if I can dig up some reference on that. I mean, to talk about mixed state teleportation will be a bit advanced for this class as such, but I can try to post some reference on Moodle on mixed state teleportation. Okay? But the idea would be the same. You would have to share an entangled pair. You will have to do some local operation on A side, do some measurement, and the outcome of that measurement should tell you something on B side. Okay? Yeah.
So, ma'am, would then the example that you said that if psi had been some half of another entanglement pair, will in that case also we would have to decompose it into pure states?
Correct, exactly. So you know that the reduced state is a mixed state, right, for an entangled state. I have not said that in
Yes.
class yet, but yeah, indeed. See, the point is the thing about teleportation is it does not break the superposition inside, right? You cannot copy the state. You cannot measure it, because if you measure, you're going to break the superposition. So teleportation provides you a way of transporting the state to a different lab without breaking the superposition. Now, frankly, with a mixed state, that question doesn't even arise, because there is no coherent superposition anyway, right? A mixed state means it is some mixture of pure states. So I would say, so long as you're able to teleport those pure states, then it's a matter of communicating a classical probability distribution over which these states are distributed. That's all, right? So by its very nature, the mixed state is not so, it's not so coherent, right? So this problem of how do you communicate does not even arise. But the remarkable thing about teleportation is you're able to communicate the superposition exactly without breaking it. Okay, is that clear?
Yes, ma'am. Thank you, ma'am.
Yeah. Okay, see you all tomorrow.
Excuse me, ma'am.
Yeah.
Ma'am, could you please explain once again the idea of coherent summation? I am a little confused about it.
Coherent versus incoherent, is it?
Yes, ma'am.
No, so the point is that what we're doing here, for example, right, where you have exactly this alpha 0 plus beta 1, where alpha and beta are two complex numbers, so there is typically a complex phase in between, right? This is a coherent superposition, right? If you want to think about doing this in a lab, for example, you will have to have, if it's a spin qubit, and you want to make this superposition, you will have to send what is called a coherent pulse, right? Which the pulse has to have a certain pulse width or a certain time, right, within which you do this, where the phase information is not lost, right? There's phase coherence in this pulse, right? Whereas if I were to think of a mixture of 0 and 1, right, which is some P1 0 0 plus P2 1 1, right? Then here it's like 0 is independently prepared or realized, 1 is independently prepared or realized, and the probabilities with which they are prepared or the probabilities with which they are realized in a measurement, for example, are given by P1 and P2. They're independent processes, but getting alpha 0 plus beta 1 is not an independent process. The 0 and the 1 state have to interact in a coherent way to get the state alpha 0 plus beta 1. But to get this mixed state, it's basically like I said, like I toss a coin, right? And every time the coin is head, I prepare 0. Every time the coin is tail, I prepare 1. That's how I get a mixture, right?
Oh, yes,
That's
ma'am.
better.
Fine.
Yeah.
Yes, ma'am.
Okay.